My name is Joe Battaglia. I'm from New York. If any of you listen to Off the Hook, I'm Redbird. Okay, so the talk today will be on magnetic stripe technology. I'm going to go over magnetic stripes, how they work, some of the fundamentals behind them, how you could build your own cheap magnetic stripe reader, just like out of junk parts, reverse engineering using magnetic stripe using this magnetic stripe reader, and a couple of other things. So I'll discuss how I got this idea first of all. If any of you have been to New York City, the fare cards that they use for the subway system are based on magnetic stripes. And basically you go up to a vending machine, you purchase a card, you know, put whatever value you want on it, buy a $10 card, and every time you swipe it through a turnstile or use the reader in the bus, it deducts your fare and you get into the bus or the subway system. You could buy all sorts of different Metro cards, unlimited cards, reduced fare cards, or whatever. And for the past couple of years, the MTA, who runs the New York City subway system, has been having a problem where people have been going into the subway system, picking up discarded cards that have been devalued on the floor. So there's no money left on it. However, they've been picking them up and sort of bending the corner and basically figuring out a way to swipe it through the turnstile and trick it into thinking that there's actually one fare still remaining on the card. And I got into a discussion with a bunch of people about this at one of the 2600 meetings, and we were trying to figure out how it works, and no one really seemed to know how it worked. I asked a bunch of people. They really absolutely had no idea. I went and asked some of the people who are actually doing it, and they had no idea as well. And it wasn't necessarily a huge problem for the MTA to begin with, because not very many people knew about it. And the people who did know about it really didn't know how it worked. They would always say, okay, well, I don't know how it works. A friend told me about it, and all I care about is that I get a free ride. Except that people started, as the knowledge started spreading about this, people would go in, jam the vending machines, you know, stick wads of gum where you would get the card or where you would insert your money, and force people to pay them to give them a ride. And you know, they would charge you like half of the fare or whatever, but it was still a problem for them. And so recently they corrected this, but I'll talk about that later. And the discussion was, okay, why is this happening? And since nobody knew, I kind of wanted to figure it out, and decided the only way I was going to do that is to be able to read these cards. And the problem was that they were completely proprietary format. There was no way to read these cards with the standard magnetic stripe reader. Every time you would try, you know, it would give you an error. Any type of standard reader would not read these cards. There was no documentation anywhere, obviously, as to how the system worked, so you kind of had to start from scratch. What I did realize, though, after tinkering with it for a while, kind of doing some research behind standard magnetic stripes, found out that, okay, well, swiping them across the read head of a standard cassette tape player, you would hear some audio, which is what you guys just cringed at. That's what it sounds like. That's what you would hear if you pass a magnetic stripe over the cassette head. So my idea was, okay, well, can we interface this to a sound card and write some software to decode it? And that's what I'll talk about today. I'm going to discuss some of the basics of magnetism. I'm sure most of you already know this stuff, but in case you don't, I'm going to go over it. Start with magnetic poles. Every magnet has two poles, north and south. I'm sure everyone in here has played with it. You put like poles together, they repel. You put dislike poles together, north and south, and they attract each other. It's very simple. Ferromagnetic materials are materials that, when inserted into a magnetic field, can become magnets themselves. The coercivity of these materials is a measure of the strength of the magnetic field required to do this. So I'm sure you've all seen, you know, people magnetizing screwdrivers so that you can pick up screws and whatnot. So basically you're making this material a magnet itself. And a solenoid is basically a coil of wire, and that's all it is. When current flows through the wire, it creates a magnetic field. And so on one side would be a north pole, and on the other side would be a south pole. If you reverse the current, it reverses itself, so the south pole is on the other side, and whatever, flip-flops. It also works in reverse. So when a magnetic field is passing through a solenoid and cutting through the solenoid, current is induced within the coil. And if you have it hooked up to an oscilloscope or whatever, you'll notice a little voltage spike every time a magnetic field passes through it. If you look at the magnetic field lines of this, which is just a standard bar magnet, near the surface of the bar magnet, you'll notice that the field lines are completely horizontal. And so if you were to pass a solenoid over the surface of a bar magnet, nothing would happen because the field lines aren't cutting through the solenoid. And this is exactly what happens when you pass a read head over an unencoded magnetic stripe. It acts just like a bar magnet. Nothing happens. You don't see anything. If you look at the junctions between two magnets, you'll notice that with attracting poles, it looks exactly like a bar magnet. The flux lines are horizontal. If you were to run a solenoid across the gap, you wouldn't notice any current induced in the coil, and you'd have no data there. However, if you run it across the gap between two poles which repel each other, you'll notice how the field lines kind of go vertical. So very near the surface, all the magnetic field lines are vertical. So passing a solenoid over that would induce current in the coil, and if you had it hooked up to an oscilloscope, again, you would see a little voltage spike every time you did that. It works with south-south and poles that repel each other. And so, okay, how do you apply this to magnetic stripes? Well, to make a magnetic stripe, first you take like hundreds and thousands of these little ferromagnetic particles, combine them with a binder, which is just basically like a glue, paint them onto a plastic card, ATM card, whatever you want to make, any mag stripe card, and expose them to a strong magnetic field, which basically aligns all of them, and you allow it to dry. So you have all these hundreds and thousands of little ferromagnetic particles which could potentially become magnets themselves aligned onto a stripe, and they're held together. Nothing can move them, whatever. They're permanently there. So that's how you make a blank mag stripe. Now, when you want to encode a mag stripe, like I mentioned before, you can take a solenoid, apply current, and it essentially itself will become a magnet. So if you were to run this over a magnetic stripe, and as you were running it over the magnetic stripe, flip the current in the solenoid, you would start creating points where, like you saw before, you would have two poles next to each other which would repel each other. And they stay there, and the flux lines stay vertical because they're held together with glue. There's nowhere they can go. So you create these flux lines. And if you were to take a read head later, run it over the magnetic stripe again, you would notice voltage spikes again, exactly where you would created those flux reversals to begin with. And it's a little bit more difficult to write to a magnetic stripe than it is to read, because you have to worry about timing, and it's not that difficult, but I'm not going to cover it here. You have to worry about timing because you don't want to encode only a portion of it, or you don't want to do it too slowly and you record off the end because you'll lose data that way. So I'm just going to discuss reading them right now. Okay, so what we're worried about right now is the waveform that you get out of it when you look at the output of the magnetic stripe read head from the point of view of the sound card, for instance. And what you see is, like I mentioned before, a series of flux reversals, which are just voltage spikes, throughout the length of the card. And the way that you encode binary data with these is you use a method called Aiken biphase. And in Aiken biphase, it's a form of frequency shift keying, the same sort of stuff that the old modems used, and you could hear it. It sounds just kind of like an old 300 baud modem or whatever. And you use this, and this is used by setting a frequency to define a 0 bit. So let's say, for instance, every 1 millimeter on the card, this is an exaggeration, you'd have a flux reversal. And on standard magnetic stripes, you have a series of clocking bits, which basically sets the 0-bit frequency for you. So the clocking circuitry within the reader can use that as a reference. So let's say every millimeter you have a flux reversal, let's say 20 times, and those would be the clocking bits for the card. Then you continue to read, and you see, okay, well, there was a spike the next half millimeter, and again the next half millimeter. That would be a 1-bit. Again, the next millimeter you would see a 0-bit, and I'll demonstrate this for you right now, and it'll be much more obvious. So just give me a sec. So this is just a standard magnetic stripe. It's a standard encoding. It's the sort of thing you're likely to come across pretty often, in your wallet, ATM card. This specifically is a Starbucks card. Just okay. So this is the output waveform right here. Okay, so like I said, this is a standard card, so the first 20 or so spikes that you'll see here are clocking bits. And that's how the clocking circuitry for the magnetic stripe reader sets itself to read the cards. So for instance, this will be a 0-bit, the next one will be a 0-bit, 0-bit, and then see how there's 2 spikes within the same period that there was a 0-bit, that's a 1-bit. So that's how Ake and biphase works, and that's how you decode the binary on a magnetic stripe. And you could sit here and you could decode it by hand, but you don't really want to do that. Okay, so anyway, so the point of this is to write a piece of software, take in the raw data from the magnetic stripe. There's absolutely no hardware involved, and decode it. You get the raw binary out of that. So the benefits of this is obviously it's not dependent on any sort of serial parallel PS2 port. You know, most laptops don't have them now, so it'll work with most laptops. All the decoding is done in software, so you could analyze proprietary formats, for example, like the MetroCard. And you could very easily decode standard formats as well. And it's extremely cheap to make. You don't have to invest any money into it. I'm sure everyone here has a broken cassette tape player somewhere where you could find one very easily. And let me go back real quick and show you how to make one of these. Essentially, all you're doing is you're taking a cassette head and connecting it directly to a 3.5mm jack. You could snip off the connector in a broken pair of headphones or something, solder it directly onto the read head, which has, depending on whether it's monaural or stereo, either 2 or 3 connectors. In the case of a monaural one, it's very easy. You just solder 2 wires. It doesn't matter which direction. In the case of a stereo head, there will be one common pin and one for the left channel, one for the right channel. It doesn't matter whether you use the right or left channel. It works just the same. So that's how you make them. It's extremely cheap, extremely easy. You could build it in less than 10 minutes if you have a soldering iron. Okay, so let's take a look real quick at the sort of stuff you're likely to see on the card. If I take the same thing and run it through the software. Okay, that's the binary from the data. That's doing essentially exactly what I just explained. Looking at the distance between each spike, from the initial clocking bits, basically setting a reference and comparing it to each spike, saying, okay, is this a 0 or is this a 1? And all it's doing is outputting the raw binary to standard output. You could take that and pipe it through something to decode the binary, and you get the exact data that's on the card. And what's nice about this is everything's documented for standard cards. There's ISO specs that you can look up, and I'll mention them later. To see all of the documentation on it. It's all very standard stuff. You can, I have this software freely available. I'll give you the URLs at the end. But it explains the algorithm to calculate the checksum, so you know exactly whether or not you have a good read or not. If I did a poor read, I would know right away. Detection failed because the checksum doesn't match up. So it's very, very reliable for reading standard cards, and there was really no effort involved in making this. Okay, so this is I'm not gonna go over this too in depth because this is the sort of stuff you could look up in the ISO specs, but this is the standard spec for magnetic stripes that you'll find on ATM cards or any standard card that you could read with an off-the-shelf reader. The first two tracks are very common tracks. You'll most likely find them on most cards. The first one, as you can see here, has 210 bits per inch. 7 bits define each character, and you have 79 alphanumeric characters. So that's the alphanumeric track. Track 2 and 3 are numeric tracks. 3 has a higher bit density than track 2, but it's very, very rarely used. I think the only place I've seen it commonly used is on airport boarding passes. Track 2 is 5 bits per character, 75 bits per inch, so you could store 40 numeric characters on that track. Okay, this is the data you're likely to find on a typical financial card. You'll notice this, the start sentinel is a character that basically says, okay, start here. This is you know, this is the start of the track. This is where you start decoding and calculating the checksum. You'll see a format code. You'll find, you know, you'll find that the format code is like B for a bank card. There's a couple of other characters that define different types of cards, but you can look all this stuff up. The primary account number, a field separator. On track 1, since it's alphanumeric, you'll find your name, another field separator, additional data, and discretionary data. Discretionary data is variable depending on the organization that's issuing the card. It's hard to tell what you'll find there. There's all sorts of crazy stuff you'll find. And the end sentinel. And that's when you know that's when you know where to stop reading for characters and start calculating the checksum, and then you calculate the LRC from that and compare it to what's next, what the next character you read is, and that's how you know whether or not you have a valid read. It's very similar for track 2, except it's only numeric data. You won't find your name on there, but you'll find pretty much the same information that you'll find on track 1, and this is again with ATM cards, credit cards, stuff like that. Okay, so for the reverse engineering bit, when you find a card that doesn't conform to any standards, it's kind of difficult to know where to start. And luckily I was able to start with the standard stuff, which is pretty well documented. Okay, so how do you do this without knowing what data is encoded on them? Basically, you want to be able to do something like write a program to parse the raw binary output and say, okay, well, parse it into something I could read, find out exactly what's on the card, what each field means, etc. And so let me show you real quick some of the differences that I found between the Metro card and standard cards, in case any of you come across proprietary formats that you want to take a look at. Okay, so I just swiped a standard Metro card from this is from the New York City Transit System, and it looks similar to what I swiped before with a standard card, except you'll notice at the beginning all those clocking bits that I mentioned before, they're not there. It starts with a 0 bit, and then here in this case there's another 0 bit and a 1 bit and whatever. And so it's not exactly the same as the other cards. Standard readers are looking for quite a few clocking bits to set their internal clock, and Metro cards just simply don't have that. Also, what you notice if you actually decode the binary and try to checksum it is that there's no LRC at the end. There's no checksum that you could do. There's no start sentinel, there's no end sentinel. You don't really know where to start and then decoding the data. And so it's really a proprietary format that's kind of lousy. So what I had to do was modify the program to ignore all the clocking bits. Basically, it takes the first bit and assumes it's a 0, which is a pretty bad assumption because a lot of times the encoded data at the beginning of the card will be a little bit weak, and you really want to have a lot of clocking bits to average it out to really find what the average distance between the 0 bits are. So ignoring all that, we can swipe a Metro card. Well, I don't want to run it through this because that'll fail. And get the binary data. That's after all the modifications. There were a couple of other differences as well that I'll mention later. And so, okay, so what do you do with that once you get all this raw data from the magnetic stripe? Well, you have to sort of find a way to analyze it. You have to get a bunch of cards to get and this is common with most types of reverse engineering. You try to get as many samples as you can with as much data as you can remaining constant across your set of cards. So what I did was I went into the subway system, bought 10 cards from the same vending machine, and what you get is you get 10 cards, you get the same value. Thank you. All the cards have the same value on it. They all have sequential serial numbers because of the batch. When they stick the batch in, they're all sequential. You purchase them from the same place. You purchase them, from the same station. You haven't used them, so the number of times you use them is the same value and everything. So when you read these cards, you'll notice that a lot of the bits are the same. You have the same value. Like I said, you have all these fields that are constant, except for the serial number field. And you'll notice that, okay, here's a field where the raw binary is increasing by 1 every time. So you can easily narrow it down to this field being the serial number field. So then you go and you say, okay, well, what can I change next? and you swipe 2 or 3 of the cards at the same turnstile, maybe you want to deduct 1 or 2 fares from each, so you'll have 3 cards. One of them has $10, one of them has 8, and one of them has 6 now. Again, the serial number field, so you could ignore that. But now the value field is different, so you can again go look and see what changed, and you see, okay, well, a couple of bits of binary have changed here. What could that be? Okay, that's the value. And sometimes it's a little bit hard to see where they start and end. But as you track more fields down, and you see the least significant bits changing, you can kind of judge that, okay, the next one is the most significant bit for the next field. And so you don't have to do it, you don't have to be that drastic as far as how much money you put on it, or how high of a serial number you could get, or so you can eliminate it, eliminate a lot of the fields pretty easily. And there's still, I mean, I found that there was a whole lot of data on these cards that most people have no idea is there. I'll show you exactly what's on them in a second. Okay, so this is track 3 of the Metro card. What it turns out is that Metro cards have 2 tracks. One is where track 3 would normally be on a standard card, and track 1, 2, as I call it, is a wide track that occupies a space that tracks 1 and 2 would occupy on a standard card. So you could set the position of the read head to either track 1 or track 2 and read exactly the same data from the card. In my case, the original reader that I used to do all this, do I have it here? Let me see if I could find it real quick. Okay. The original reader that I used when I first started developing this was exactly what I mentioned before. It was 3.5 millimeter jack, cut off a pair of headphones. This is a cassette tape head with a bunch of electrical tape around it. That's it. What you have to do with this is kind of a pain. You have to kind of, clamp the card down or put a weight on the card and use a ruler to align it and sort of drag it along the magnetic stripe. And I could try it now, but I don't really have anything to do it accurately with, so it'll probably take me a couple of tries. But this is all you need to read magnetic stripes. It's really not complicated at all. What I have here that I'm using to demo today is a surplus reader that I got. This actually came with a TTL decoder, which outputs TTL logic levels for each bit that's decoded. But I bypassed all that circuitry and just patched in another 3.5 millimeter jack directly to the read head, exactly like I did with the other one, except now I have this nice track to slide the card through, so it's much easier. I don't have to sit there with a ruler and play with it like that. But and it works really well and really reliably. The only issue is I could only read 1 track at a time, and to change the head I have to open it and move the head. But I'm sure one of you guys who are good with mechanical stuff, can develop something to switch the head. So anyway, that's what I'm using to read the cards. You could find these surplus readers for like $5, or on surplus sites where people have bought too many, or companies are discarding them and using something else or whatever. They're very cheap, very easy to find, and you could easily modify it to use with this application. So anyway, some of the data that was on track 3 was a 15-digit start sentinel, 15-bit, I'm sorry, start sentinel. The next 4 bits define the card type. The next 4 I don't really know. The next 4 define the expiration date. The next 4, again, I don't know. There's quite a few fields on this track that I don't know. Track 3 stays constant across all the reads. So when you go from, if you go into the bus or you go into the subway, all this data stays constant. None of this stuff changes from the time that the card is produced till the time that you finish using it. Again, serial numbers on there, and then a couple of other things that I don't know are on there as well. And track 1 and 2 is much easier to narrow down because this is all the data that changes. And the method that I used before, like I said, is just trying to keep as much of this constant and changing 1 at a time, which allowed me to eliminate a lot of fields. So it was weird. The time was split between two fields on the card. The card subtype, which basically told whether or not it's an unlimited card, a pay-per-ride card, or any of the other number types of cards that you can buy as a regular citizen. There's a couple of other kinds of cards which are defined by the card type set on track 3, which are student cards, reduced fare cards, employee cards, and stuff like that. Again, the number of times the card was used, the expiration date, whether or not you had used it for a transfer, the last time you used it, where the last place you used it was, and where you purchased it from, and most importantly, the value of the card. And now getting to back to the story in the beginning, I was trying to figure out, okay, well, why were you able to bend the corner of the card and get a free ride in the subway? It didn't make sense. Well, it turns out that on track 1 and 2, halfway down the middle of the card, there's another abnormality in the encoding scheme, whereas there's a half a bit. Now there's a 0 bit, which is a full length of the clocking bit. There's a 1 bit, which is half the length of a clocking bit, and then there's half of that, and that sort of divides the card into 2 records. So the first record, for example, when you buy the first and second record, for example, when you buy a $10 Metro card, will be set all the fields exactly the same on the first and the second record. The card value will be 10 on both. But when you use a card for the first time, the first record will change to say that you have $8 on the card. The second record will still remain the last transaction. You keep doing this until the card's empty, and it turns out that when you get to the end, half the card says you have no, has no value. You have no more. You can't enter the subway. You can't enter the bus. You have no value on the card, and the other half still says you have $2. This was probably done when they changed, when they were doing the experimental MetroCard system, and everybody was having a hard time getting into the system. Like I said, it's kind of a crappy way of doing it. You don't have very many clocking bits. You don't have a lot of stuff that you have in standard cards to ensure that you have proper reads. And so people were standing at the turnstiles for 20 minutes trying to get in with their MetroCard, and it just wasn't working. And so what I believe the result of that was for them to implement this, where they have 2 records for redundancy. Again, where the second record is the last transaction and the first record is the current transaction. So what happens is you bend the corner of the card, right, and you're creating a read error in the last in the current transaction. So when you swipe the card, it'll give you an error like, okay, please swipe again in this turnstile. You swipe it again, and it'll give you the same error, and then the third time it'll say, okay, fine, I'll accept the card. I'll assume that the last record is valid, even though it's not, and it'll let you into the subway, even though you have no value on the card. And so that's what it turned out to be after all this work trying to decode these cards. The MTA recently came up with a solution for this, which was to update the firmware in the readers, and they didn't want to invalidate all the cards that they had been issued. So their trick was to treat the last swipe, whereas you have less than 1 fare remaining after the swipe, as a transfer. So they make you actually swipe it twice in the turnstile before they let you in, which is interesting because they must have updated something else to allow buses and subways to sense whether or not it was actually a transfer, which I haven't found yet, but it does set the transfer bit the second time. Anyway, so that's the solution to that. What are the implications of this? Well, first of all, again, it's extremely cheap to make. You can really, like I said, make this in minutes and explore different magnetic stripe cards that you have laying around. You could view all these proprietary the data on all these proprietary cards, and again, you can expose poor security through obscurity models and sort of see the security weaknesses in systems that were really not able to be analyzed before. This is where you can get the article text. They were published in 2600 magazine in the spring. If you guys want to write down these URLs before I show a couple of the Metro cards. Okay, well, I think they'll be on the wiki or something. Okay, so this is an example of a standard Metro card. So I'll mute that. Okay, so you see there's 2 records on here. This happens to be a 30-day unlimited card, so there's really not too much you could do with it. I'm reading track 2 right now. I'm not going to switch to head to read track 3. But if I did read track 3, it would output exactly what you saw on the slide. It would just give the serial number of the card and all this non-interesting stuff. It shows the time of the last use. It shows how many times you used it. In this case, I usually find my Metro cards on the floor. So I come across all this weird stuff like somebody buying a 30-day MetroCard for $70 and using it only 3 times. Yeah, it's kind of strange. You can also look up the last place you used it. There's no database that I could find that correlates this information to anything that's publicly available. But kind of by brute forcing it, you can create a database of places where you know the card has been used last. I'm sure there's something on here where I have. Okay. Well, first of all, let me show you a standard card. Okay. So this is a card that has, I think, $13 remaining, something like that. Okay. And notice how the reason only $1.50 was deducted is because the last use was at a path station. The path stations only charge $1.50. You can see this is a standard full fare card. On the first record, the value is $15. On the second record, the value is $13.50. And sometimes these reverse themselves. I'm not sure exactly what determines whether or not they're going to write the first record on the front or the back of the card. But usually the current record is on the back of the card and the previous record is on the front of the card, although sometimes that does change. And the way the machines probably tell the difference is you can see the number of times used is greater in the field that has the latest data on it. Anyway, so you can see how here, when a value is deducted from the card, it keeps the previous data in the last record. And so if you look at a card, if you had swiped a card with $2 on it a couple of months ago before they applied the firmware patch, you'd see this, where record 1 has $2 and record 2 has $0. And to any machine in the MTA, it would show that you have no value remaining. But on buses and subways, if you create a read error on the second track, in the second record, I'm sorry, it will only read the first record as a fallback because it doesn't want to, they didn't want to create delays again at the turnstiles, and you'll be able to do that. The problem is you can't destroy the stripe. It has to be able to write back and verify that it wrote back to the card before you can actually enter the subway. So what you would do before is you would bend the card, you would swipe it once, it would get a read error, you would swipe it again, you'd still have a read error, and then you'd unbend it so that it could write back to the card and verify that it successfully wrote back, because the only place you could use the card again is at that same turnstile. You do it again, and it writes back to the card that you have no value remaining on both records, and then it lets you into the subway. So you could only do it once per card, but this was sort of a common thing, and nobody really understood how it was happening. They applied the patch, like I said, so that if you have $2, if you have less than 1 fare remaining after you've swiped the card, so that goes up to $3.99, I think, if there's a value up to $3.99 on the card, you swipe it again, and it will make you swipe it again and rewrite that record on both, rewrite the current record on both records. What they didn't do is apply that universally, so that if you have $10 remaining on the card and you swipe it once, you have $8 remaining, you can do the exact same thing with $8 remaining on the card, swipe it again, and the turnstile will write back that you have $10 remaining on the card. So you could kind of keep doing this regardless of whether or not they updated the firmware or not. And it's just kind of one of those things that they say they fixed the problem. Nobody's really going to investigate it because they figure, okay, fine, the MTA knows what's happening now and they fixed it, and this will never work again. But unless you actually know what data is on the card, you can't really decide whether or not there's any other ways to exploit it. In this case, there still is a way to exploit it. Whereas, like I said, if you have more than 1 fare remaining on the card after you swipe it, and so they still haven't really fixed the problem, and it's kind of one of those fundamental flaws that without reflashing everything and making all these cards invalid, they're not going to be able to fix. But it's just one of those things. There's a couple of, stories I can tell about weird things that I found. For example, at my school now, the school that I go to, we use mag stripes on our identification cards, and what they have across the town is sort of point of sale machines throughout the town that my college is in, linked to each student's ID card, and so you can basically swipe your ID card and charge a meal to your card or charge a drink or whatever. And what happens to be on the card is a student identification number, and that happens to be your social security number. What they do across campus is use this for entry into the dorm rooms, and some people have access to certain dorm rooms, other people have access to other things. The campus police obviously have access to everything. So if you can get your hands on one of their social security numbers, you suddenly have access to every building on campus. So there's, by looking around and seeing what's on every card, you could kind of see how things could be manipulated. Another security thing that they have is if you lose your card, they append an additional number onto your ID. So, for example, if I lost my card once, I would have my social security number and then 02. If I lost it again, I would have 03. And so it's really crappy as far as preventing fraud, because if any student was to come across this and start cloning cards, it's very easy to get people's social security numbers. You could withdraw funds from their account. You could get into their dorms. You can do all sorts of things like that. In the student computer center, they have printers that require you to swipe your magstripe card in, with all built into the keyboards. And if you create an error by typing a digit and swiping the card, the social security number and the appendix to that come up on the screen. So you can get people's information that way. If you're quick, you can type in somebody's social security number and hit enter, and it'll think that the magstripe reader read it, but it really didn't. So you don't even have to make a new card with the student's information on it. So there's all these weird things that you can do with this. Mainly the simplicity of building a reader, with spare parts and whatever. Last time I had a lot of questions, so I'll stop here. And if anybody has questions, feel free to ask.
Get any solution to actually write onto the card?
I don't have anything that works reliably right now. It's possible to. I don't have the software on with me right now, but I was playing with generating the waveforms for encoding your own stripes if you want to. It's really not hard to write the software, and it's really not hard to get the waveform generated properly given the raw binary data. But it is hard to get the timing right. I'm not so good at building things. I can, you can find a solution where you have a motor rolling the card through at a constant velocity, so you could get very accurate timing that way, or you can just do trial and error, which I've been doing, and it doesn't work so well. To do this, you need an amplifier at the output of your sound card. You're not just gonna write to a card using the output of your sound card. You'll fry the final amplifier or whatever. But it's possible, but I wouldn't recommend doing it. You could build a little audio amplifier to do this out of like an LM386 or something. That should provide enough power for most loco cards. You may also have to bypass the output capacitors for your sound card. There's capacitors at the output of your sound card which prevent DC output. So if you can bypass those, you can get a nice DC waveform out. It's hard to do on a lot of sound cards now. You can do them more easily on the old ISA sound cards and stuff like that. But it's something to play with. You can certainly do it. It's just not as easy as reading. It's not something you could do in a half hour, I don't know, on a weekend or something. But yes, it can be done. You can write the software to do it. It's just a matter of creating the hardware to accurately write to the stripe. Any other questions? Don't be shy.
1 minute, please wait for the microphone.
The people who run the public transport system, did they try to stop you from spreading this information?
No, I never got. I have a feeling that if I was going to be contacted about it, I would have been contacted before I published anything. I went on off the hook with some of the information before I ever published the article with the alias Redbird, kind of because the old subway trains that they were phasing out happened to be called Redbirds, so I kind of used that. Nobody ever contacted me then through the show. Nobody's contacted me from the MTA since. I've been contacted by, like cops and private investigators and stuff like that, just asking about it and stuff like that. But I don't really like dealing with those people. But nobody from the MTA has actually contacted me, and I'm not sure that they know about the second way of card bending, which is, like I mentioned, if you have more than one ride remaining, because most people aren't willing to mess with their cards if they know they have value on it. So for their purposes, it's probably effectively solved the problem. But from the standpoint of whether or not an exploit still exists, it's certainly still there. You got to be careful when experimenting with this kind of stuff. I was in the subway when I first started doing this, and I was playing with the turnstile and some cards and whatever. I was down there for maybe 5 minutes, and I had gotten the turnstile to open a couple of times and kind of just walked through and walked immediately back out. I had no interest in actually going anywhere. And two plainclothes officers came down and were like, "Let me see your MetroCard." I'm like, "What?" I had like 200 of them in my pocket, and I gave him one, and he was like, "Oh," and they ended up giving me a $70 ticket for turnstile manipulation, which I don't even know if that was something that they've ever done before, but I just paid it. Any other questions?
Yeah, I have a question. Have you found out if you're able to add money to your card at the OTA system?
Okay, well, like I mentioned, there's a couple of fields on the card that I'm not exactly sure what they are, and I have a feeling the last one may be a checksum that I don't know how to calculate. So as far as actually adding anything to the card, I don't know how to do that. I can't do that right now. As far as copying cards, you can very easily make a magstripe copier. Basically, you have a reader in parallel with a writer, amplify the output from the reader, and swipe a blank card through, and you could very easily make a copy. If you want, you could copy cards. There's the checksums are already calculated for you. Other than that, no, I don't know how to make a card from scratch with the values that I want on it. Let me explain a little bit. The whole MetroCard system is actually offline. It has to be that way because the buses aren't constantly connected to the network. And if there's a network failure in the subway, you can't have millions of passengers stranded until the network guys get it back up again. So the whole thing operates offline. However, they do have the ability to track and disable serial numbers. So if they notice anything funky with a card, like, wow, the same serial number's been swiped 5 times and each time it has $10 remaining on it, they'll disable it. And apparently there is a way to know whether or not this is happening at one particular subway station. They have each token booth has computers, and apparently there's a way to track this. I don't know the details of it. I've only talked to a couple of MTA employees, and they didn't really know all of the details about it. But I've heard of people getting in trouble for playing with this. When the MTA system first came out, someone had copied a card onto an 8-track tape. Glued a piece of 8-track tape to a piece of cardboard, made a copy exactly the way I just explained, just amplifying the output from one and copying it onto the other, and swiped it through and got arrested actually because a cop saw him swiping a piece of cardboard. But I have heard other stories of people getting in trouble for making copies of MetroCards, which really isn't hard to do, and swiping it a bunch of times. My purpose wasn't to get arrested; it was just to find out how it works. So I don't know how easy it is to track. Any other questions? And okay, well, I guess thanks for your time, and if you have any other questions, just come up to me.